Hello everyone. In today's lecture we will discuss about the shear mode piezo actuator. So if you see this figure, as I have shown this figure in the last slide also, so it illustrates a schematic connection and its deformation in a shear mode piezoelectric actuator. So basically, if you talk about what is piezoelectric actuator, that when the potentials are applied on the terminals of a piezoelectric material, then a deformation comes in terms of the mechanical force. So here, when the deformation is taking place in a shear mode direction, or the forces are generated on the tangential surface of a material, then it is considered as shear mode piezo actuator. In this case, it is important that the component, basically the piezoelectric component, need to be horizontally polarized. It is the criteria that in which direction we have to bring the elongation or kind of a deformation. So if we do not kept it in the horizontal direction, then the shear mode force will not generate it. Shear mode deformation will not be developed. If a voltage is applied in the horizontally polarized material, then shearing force is developed. This shearing force will further cause the element to shear. So shear means the forces are going to be applied in on the tangential direction. So you can see that previously this dotted line shows that the figure was kept horizontal, and when the force is applied, so it has come to this direction. Now this is the slant is the material gets slant, a deformation comes in the material toward this direction. Now because of this shearing effect, the element is subjected to a kind of a displacement. Generally we call it as a kind of a deformation, but when a material is moved from one place to another, that time we consider it as a displacement. This displacement is given by the equation D is equals to capital D is equals to N small d into V, where capital D is the length of the displacement, which we are going to calculate here, that how much the material is moved. Small n is the number of layers, V is the applied voltage, and D15 is called shear mode piezoelectric constant. So this D15 generally depends upon a type of material which we are using, and V is the voltage that we apply on the cross terminals. So one point is to be noted that displacement here is independent of the dimensions of the material which we are using here. Therefore, in case of MEMS, very thin layers and small structures can be designed. So when we are working on micro level, that means from macro, when we are coming to micro, definitely the dimensions are going to be changed for a material, for a piezoelectric material. But here those dimensions are not affecting the basic working of the piezoelectric actuators. Thus, these kind of layers and small structures can be used for various range of application. So, the scientist Fujitsu has developed a typical shear mode piezo micro actuator that can be used in the hard disk drive of a computer. In traditional non-MEMS actuator system, the servo bandwidth is limited by the mechanical resonance of the carriage, coil, and ball bearing pivot. That means the amount of deflection which we are going to be created with the help of the applied voltage terminal, that will depend, or that can be limited by the mechanical resonance of the carriage, coil, and ball bearing pivot. That means how much the other mechanical components will allow the piezoelectric material to take motion. Some types of micro actuators have been proposed as possible ways to attain a wider servo bandwidth. So this servo, when we are talking about, it is the servo motor which is used for some kind of actuation purpose. The micro actuator design for the HDD hard disk development applications can be of three types based on the way actuator drives the component. So that can be driving a head suspension assembly, driving a slider, or driving a head element. When we talk about the head suspension driving micro actuator, they are easy to manufacture. They are expected to be used in SGDs in the near future in spite of their poor mechanical characteristics. So compared with the slider and head element driving types. So this is to be noted that head suspension driving application or kind of a micro actuator design is of more use than the other two, slider type or the head element type. The detailed structural design is shown in figure 5.21. I'll come to this figure in the next slide and I'll explain you this one. But before coming to this, let's go through that. Its specifications are given here that the mass of the head suspension is 62 mg, stroke is 0.5 micrometer. So here you can see that how small deflection we are achieving because it's a MEMS component. Resonance frequency is 9 kilohertz. Capacitance is 650 picofarad. Shock resistance is greater than 950 G. Dimensions are given as length, width and thickness 2.2 mm, 1.3 mm and 0.15 mm respectively. So how small is the component? Complete assembly. So it's a kind of actuator, piezoelectric actuator or shear mode actuator. So mass is given as 62 mg, D15 is taken as 8.4 e raised to the power minus 10 meter per volt, and its range is plus minus 25 nanometer with plus minus 30 volt mechanical advantage. That means output to the input ratio, it is 20 times. Displacement at the head is 1 micrometer. The complete design, which I'll show in the next figure, it consists of a carriage arm, stator plate, electrodes, single layer piezoelectric element, head mounting block, head suspension. The micro actuator has a high resonant frequency of 9 kHz with peak gain at resonance is 20 decibel and with high shock resistance. These parameters are considered as the required mechanical characteristics of a good actuator. Now coming to the structural design, the first component you can see that it is a head suspension assembly, 30% pico slider. The second component is the head mounting block, which has a hinge connection which allow the head suspension assembly to rotate. Then electrode, two electrodes are shown over here which work as a positive and negative terminal, and there is a single layer piezoelectric element between them. So this electrode provides a potential voltage across the terminal of this single layer piezoelectric material. Then there is a stator plate which allows this complete upper assembly to fix with the piezoelectric actuator or the carriage arm. So the front view is also shown that it has a rigid base, rigid shaft, there is a disc, micro actuator, sensor and arm. So the figure number A is a precise positioning of the hard disk drive including the various paths, and figure number B shows the integrated into the hard disk drive. That's all for today. Now we'll continue with the next lecture about more mechanical sensors and actuators which are used in the MEMS.